Let's explore through the three examples problem of optimizations. So the first example says that a closed cylindrical can is to hold 1 liter. So we have a cylindrical shape. How should we choose the height and radius? So here is, let's you suppose that we have, yes, a cylindrical can. So we need to know the height. Here is the height and radius, so circular section, so there is radius r. To minimize the amount of material needed to manufacture the can. Okay, so we are concerned with the surface of the can. Okay, so let's evaluate the surface. So if I open my can, I will have the largest rectangle that covers the lateral surface. Then we have two discs, okay, two areas to be considered. So the total area, so let's say this one is a rectangle, so this is the height, okay, and to the longest side here has a perimeter of 2 pi r. Okay, so that the area, the shaded area here, if I shed this part, okay, so this area will have let's write e1 is, so height times, okay, so this side times this side will give me, so 2 pi r h. Okay, now what about the other cylindrical, the cylindrical part here, there's to have the area, let's say E2, okay, so this one E2 with pi r square. Okay, so the total area, AR, so let's first, yes, total area of the can, okay, so will be, so 2 pi r square plus 2 pi r h. Okay, now the question is, how should we choose the height and radius to minimize the amount of material needed to manufacture the can? So we can see, yes, look at our area as a function of RH, and we are concerned by finding the minimum area, okay, when R and H R, of course, R quantity, a positive quantity, H also is positive quantity. What else? We need also that the quantity held by this can is to hold 1 liter exactly. So we know the volume. Okay, so the volume, we know that the volume, what is the volume of the can? So let's write it somewhere. The volume here is equal to the area, the basic of the section, and times height. So it's pi r square h. Okay, so this is the volume. So we impose the condition of this quantity to be 1000, let's keep it like that, centimeter cube, okay, as unit. So I'm looking for, so the problem I'm setting is, how can I minimize the area when I need when choosing R and H, so that also I need to add this condition, pi r square h equal 1000. Okay, so this is how I'm setting my problem. So I can write it differently and say it's the same to say minimum ARH when RH belongs to a set S. And my set S here is the set of all possible values RH, R positive, H positive, and also they are linked by the following relation. Okay, so you see how it goes. Another way we can, this is the first formulation. I can also suggest another formulation. Instead of taking this set like that, I can isolate H, express it with respect of R, for example, and reduce my problem into one unknown. So I can say I would like solve the problem in R only, okay, over another set S, where this time my S is the set of R. R must be positive, and what else? And yes, and R. Uh, what else? Yes, but yes, that's all. R positive. I think it's enough because I'm including the information H here. It's R, the first function, that is 1000 over pi r square. Okay, so that's all. So that I have a new function to consider, that is 2 pi r square plus 2 pi r. So if I simplify, I will get then 2 h over 1000, so 2000 h over r. Okay, so this is my new function. You see, if you look at this, your set here, the particularity of this your set here, it's part of, it is included in the plane, while here it is included in R. Okay, here it is exactly an interval, here it's a curve, part of a curve. Okay, it's part of curve because the equation is h equal 1000 over pi r square, so it's a curve. Okay, so here S is a curve, plane curve. Here S is an interval. Okay, here your function f a is function of two variables, function of two variables, and here f r is a function of one variable, Okay, so here it is. So it's not our purpose to solve the problem, but just identify some characteristics of an optimization problem. So let's have a look to the second problem. Second problem is a diet problem. So it says that one can buy 4 types of elements where the nutritional content per unit weight of each food and its price are shown in the following table. Okay, the diet problem consists on obtaining at the minimum cost at least 12 calories and 7 vitamins. Okay, so we would like to know the price, okay, the total price of the food, so how much we could pay to get the best of the elements. Okay, so let's set u, we will call ui the weight, okay, the weight of the food of type I, of the food of type I. The total price of the 4 elements consumed is given by the function, is given, so total price of the 4 elements, consumed is total price. So type 1, the price is 2, so we have 2u1 plus 2 times u2 plus u3 plus 8 times u4. Okay, so it's, let's call the price of u1, u2, u3 and u4. Okay, by weight. Okay, by unit weight we have $2, let's say, by unit weight, and we don't know how much we bought. For u1 weight we will get 2 times u1. Okay, like that. Now our purpose is to maximize, minimize. So we want with less money, less price, less price to get the maximum of vitamins and calories. So what to ensure? So now to ensure 12 calories, we need to satisfy then. So calories, we can get 2 calories for type 1, 1 calorie for type 2. So we will get 2 times u1, 2 times u1, plus we can get 1 times u2, plus 0 times u3, plus 1 times u4. We need at least ensure 12, so we need to be at least 12 and greater than 12. Okay, 12 calories. Then to ensure, the second condition was about vitamins. We need to ensure 7 vitamins, so we need to ensure 7 vitamins. So we need to we will express this as the following. So in the food, if we, for with weight u1 for type 1, we will get 3 times u1 vitamins, 3 times u1 plus 4 times u2 plus 3 times u3 plus 5 times u4. We must ensure to have at least 7. Okay, so now the problem we are setting, we can formulate our problem. Okay, we can express the problem. The problem is to minimize the cost, okay, the function fu1, u2, u3, u4 over the set S. What is my set? Is the set of all possible weights u1, u2, u3 of the different four types of food. Okay, so that I ensure the 12 calories to u1, so the u2 plus u4 greater than 12, and the inequality 3u1 plus 4u2 plus 3 u3 plus 5 u4 greater than 7. You see, so we have again to minimize function over a set. This set this time is part of R4. Okay, so it's a set that we cannot visualize in real space, the usual dimension we know. Okay, and the function also is a function of 4 variables. Function of 4 variables. Okay, so here is, yes, and you can imagine if you have more types of food, okay, and you know their calories and the vitamins they have inside and their price, you can get a problem, more complex problem, by increasing the number of variables, okay, and number of constants of inequalities of the set. Okay, so let's explore now the last his last example. Let me make it bigger, this one. Okay, so it's about an economic problem. The previous ones also are about economy. So if we know that X units of capital and Y units of labor are used, a company can produce XY. So we have a production function, P production function. So the production function, so it is, they said it's 6 times y units we can produce. Capital can be purchased at $4 per unit, and labor can be purchased at $1 unit. A total of $8 is available to purchase capital and labor. So it's a simple problem just to illustrate an economic problem. So what is that? That means this information we can interpret it as we have four times labor x units of labor plus 1 times um, now now of capital, 4 times x of units of capital, and 1 times 1 times y units of labor must be. So in total we can spend only $8 up to the maximum. So we want help the firm to maximize. So we want to maximize the production function, okay, which is, now we can see it as a function of two variables. So p of xy equal xy over the set under these on. Okay, so we can say we have a problem like this one. Yes, let's continue here. Maximum of p of xy over xy belonging to S, where S is the set of xy. They are positive, yes, y positive, or equal 0. We can include maybe, or positive strictly, let's say strictly, such that we need to satisfy this limit of money we have, okay, to spend. So you see here, this time we have a function of two variables, and our set is subset of R2. So it's a region in the plane. Okay, you can even here we can graph it, and it's much easier to visualize. So each of these problems, if you remark, involves a function and involves a set in different dimensions. So this is mainly and also we need also sometimes to minimize. So sometimes we were focusing on minimizing. Here also it was about minimizing, and here about maximizing the problem. So either we have to maximize or minimize a problem. So that's why in following sections we will need to know more about these functions. We need some, any problem optimization will be connected, so related to will depend exactly on the function that we call objective function, and the set of the constants involved, okay, the set S and the function. So we need to tools about the function. We know some tools, basic tools, and for sets also we will need to we will be able to work in a category of sets that will be that we need to develop our theory of optimization.